Now we're going to look at a special type of linear systems called homogeneous linear systems. And those are systems where the constant part in each equation is 0. So I'll actually use previous linear systems that I had, and I'm just going to change the constant part to 0. So previously we had the following linear system. So previously, I mean, if you look in the previous video in that section, we had this one, and the corresponding homogeneous system to this system is obtained by setting the constant part to 0. And we also looked at a linear system that's very basic, and that's form of only one equation. Previously it was 5, and now I'm gonna make it into an homogeneous equation, and I'm going to assign the constant value of 0. So those are two examples of one homogeneous system, one homogeneous equation, and I'm going to recover the solution set in each case. Let's start with the first example. So maybe this is equation 1, this is equation 2. So what I will do here, I will do equation 2 minus equation 1. If I do this, 4x minus 4x cancels out. I get 2y plus 9 minus 3 is 6z is equal to 0. Of course, this part is very easy, right? No matter what you do with the zeros, everything stays 0. Is equal to 0. I'm going to maybe solve for y. And I finally get y is minus 3/2 of z. Therefore, if I let z equal to t, then y is going to be equal to minus 3/2 of t. And I can also solve for x, and 4x minus y. So maybe I look at the so this is replacing in 1. And 1 gives what? 4x minus y plus 3z is equal to 0. So 4x plus 3/2 of t plus 3t is 0. Okay, small problem. I don't know why I wrote 3/2 up there. 6 divided by 2 is not 3/2, it's just 3. So minus 3z here. Let's correct this. So this is minus 3t. So this is minus 3t. So this is just 3t here. All right, okay, this is better. So 4x plus 60 is 0. So 4x is minus 6t, and x is, okay, minus 3/2 of t. So this is why I got confused. X is minus 3/2 of t. So finally, what's my solution set? The solution set is x, y, z is equal to minus 3/2 of t. This is x minus 3t and t, which I can write the following way by factoring the t out of the vector. So this is my solution set. What's the geometric description? Try to get it. Well, it's a line, because the vector here multiplied by t will allow me to move in any along this direction, and basically we're starting at the origin here. So it's a line passing through the origin. You can write that down if you want to. Line passing through the origin and parallel to the vector minus 3/2, minus 3/1. Sometimes we also like to say pointing in the direction of the vector minus 3/2, minus 3/1. So that's the geometric description. It's a line. Remember, we had obtained this previously. Well, no, because we had a different system, but Same goes here, right? We've got basically two planes. The only difference is that these planes now are passing to the origin, but they're still non-parallel. So you've got two planes that are, you know, intersecting along a single line here. So that's the equation. That's basically the vector equation of that line. Let's look at a solution of the other system. Actually, it's just one equation. In this case, we're going to let y equal to s, z is equal to t, because you know, if I want to recover one point here, that's probably what I do, right? I assign, let's say, a value of y, of 0 to y, I don't know, 1 to z, and then solve for x, right? To get the x coordinate of that point, I get -7 here. So -701 would be a point. So this is exactly what I'm going to do now, but very generally, so I'm going to assign this arbitrary value s to y, arbitrary value t to z, okay, where s and t are some real numbers, and solve for x. So if I solve for x, x is going to be, well, maybe let's replace immediately s and z by t, and I'm going to solve for x. This is, I tend to write same thing for 7 and z, which annoys me. Okay, like that. This is x. So the solution set is going to be x, y, z is equal to 4s minus 7, did it again, 7t for x, s is t, z is s, y is s, z is t, and I can split that into the different into two different vectors, essentially. One that contains the terms including s, and the other the terms including t, and factor out the parameters. So it's going to be s times 410 plus t times -701, like that. So what do I get here? I get a plane passing through the origin, because it's basically 0, 0, 0 plus, so this is my point 0, 0, 0, plus two vectors. So the s times v1 plus t times v2, it allows me to move in a plane containing these two vectors, and that plane passes through the origin. So it's a plane passing through the origin containing those two vectors. You can write that down if you want to. That's the geometric description. But this is not what I really wanted to look at. What I want to look at were the solutions. You know, I told you that previously the values, maybe if I rewrite them, the values for my constants were 3 and 5 here, and here it was 5. And let's look at the solutions we had obtained in this case. So I'm going to write it in red so that you can compare. Previously, with the constants that we had, our solution set was x, y, z is equal to 1, 1, 0 plus t times -3/2, -3, and 1. So what's the difference here? The difference is that there was a line passing through this point, but it was still parallel to that vector. And in fact, this part here, this solution set for a homogeneous system, we find it here. So what we have here is what's called a particular solution. It's the solution you get by letting t equal to 0, right? If you assign t to 0, you get the solution 1, 1, 0. So this is our particular solution, specific solution. And this, all this, it contains the solution set of the homogeneous system. The corresponding homogeneous system, the one we get by letting 3 and 5 be 0 and 0. And previously here, for that non-homogeneous equation, previously what we had obtained was xyz is 5, 0, 0. So that was a specific solution to our equation. Remember, like if you assign x 5 to x and 0 to y and z, you do have a solution, right? So 5, 0, 0 was a specific solution. So once again, that's a particular or specific solution. And after that, we had s times 4, 1, 0 plus t times minus 7, 0, 1. So you again have the solution set of the corresponding homogeneous system. So there are two things I'm going to write down. One is a small note. Homogeneous systems are always consistent because 0, 0, 0 is always a solution. So going back here, if you assign x is 0 to x, y, and z, of course you're going to get 0 on the other side. And same goes here. If I assign values of 0 to x, y, and z, of course I'm going to get 0 on the other side. So I always have a consistent system with an homogeneous system. So since assigning 0 to all variables gives a solution, all homogeneous system are consistent. So that's a small note, right? So in fact here, there's always this hidden particular solution, right? Before this, you can put 0, 0, 0. Before that one here, you can put 0, 0, 0 plus the other part, right? So you always have 0 as your particular solution, or as a point that's passing through your plane or your line, or whatever. Second thing is a theorem. A theorem is basically our observation here. We haven't proved it. We're going to prove it later on, but essentially what we observe here is always going to be true. So whenever we have a system that's not necessarily homogeneous, it's going to be written down in the form of a particular solution, which is essentially obtained by letting the parameter or the parameters be equal to 0. So particular solution, and the other part is always going to be the solution set of the corresponding homogeneous system. So the system we get by replacing all constants by 0. So this is a theorem. So I wrote it down. So the general solution, or what's also called a solution set of a linear system, any linear system, is the sum of a particular solution and the general solution of their corresponding homogeneous system. So what's the corresponding homogeneous system? Is the one you get by replacing all these constants that are maybe non-zero by 0. That's the only difference.